MLE behaves very much systematically in some family of distributions. MLE is very much regular and systematic with the general forms of those family of distributions. The most popular among those family of distributions are one parameter exponential family and multi-parameter exponential family. Besides, power series distribution family, polynomial type exponential family, etc. can also express the general form of their MLEs in a most regular way. In this module, we start the discussion with MLE under one parameter exponential family of distributions. Suppose, based on a random sample of size n, the joint PMF or PDF can be expressed as p theta x curl equal to e to the power q theta into tx curl plus c theta plus dx curl, where theta is the real valued parameter and x curl is the vector of random realizations. Moreover, q theta and c theta are the function of theta and tx curl is a statistic based on x curl and dx curl is a function which is necessarily independent of theta. Also, suppose the joint PMF or PDF p theta x curl satisfies the following two assumptions. Number 1, the first two derivatives of the function q theta and c theta exist and are continuous. Number 2, a function I theta equal to expectation of del theta log of capital L theta square exists and is positive, where capital L theta is the likelihood function of theta based on the random sample. Then capital P, which is a collection of such joint PMFs or PDFs over theta belonging to the parameter space capital omega, is known as one parameter exponential family. Check that for this family of distributions, expectation of tx curl equal to minus c prime theta by q prime theta, where c prime, q prime, etc. denotes the first order derivative of the function c theta and q theta, etc. As an outline of the proof of this result, we can start taking expectation on q prime theta into tx curl plus c prime theta. Necessarily, this is equal to integration q prime theta into tx curl plus c prime theta whole multiplied by p theta x curl dx curl, where p theta x curl is the joint PDF of x curl belonging to one parameter exponential family. Now, it is easy to note that the integrand of this integral is nothing but the first order derivative of the PDF p theta x curl with respect to theta, and as a result we can say that this integration is equal to integration del theta of p theta x curl dx curl. Now, as integration and differentiation are interchangeable here, so interchanging their order, the expectation is equal to del theta integration p theta x curl dx curl. Now, as p theta x curl is the joint PDF without loss of generality, so under integration p theta x curl dx curl is equal to 1. As a result, expectation of q prime theta tx curl plus c prime theta is equal to del theta of 1, and that is equal to 0. That means expectation of tx curl equal to minus c prime theta by q prime theta. Similarly, we can establish that variance of the statistic tx curl under theta is equal to q double prime theta into c prime theta divided by q prime theta minus c double prime theta. Now this whole expression is finally multiplied by 1 by q prime theta square. As an outline of the proof of this result, we can start with the second order derivative of integration p theta x curl dx curl, and that is necessarily equal to 0 because integration over p theta x curl dx curl is equal to 1, as p theta x curl denotes the joint PDF without loss of generality. From this expression, we can say that under integration it is del theta of p theta x curl dx curl, and that is equal to 0, as integration and second order differentiation are interchangeable like the previous case. This implies integration del theta into within bracket q prime theta into tx curl plus c prime theta whole multiplied by p theta x curl dx curl equal to 0. This implies integration q double prime theta into tx curl plus c double prime theta whole into p theta x curl dx curl plus q prime theta into tx curl plus c prime theta whole square into p theta x curl dx curl equal to 0. This expression is basically obtained just by the differentiation within the sign of the integral with respect to theta. Now this expression can be written as expectation of q double prime theta tx curl plus c double prime theta plus expectation of q prime theta tx curl plus c prime theta whole square equal to 0. The second expression under expectation can be simplified by taking q prime theta whole square common, and it becomes within expectation tx curl minus of c prime theta by q prime theta whole square. But just remember that minus c prime theta by q prime theta is nothing but expectation of tx curl. So within expectation we have tx curl minus expectation of tx curl. As a result of the fact, the second expectation is basically nothing but variance of tx curl. So the whole expression now becomes q double prime theta into expectation of tx curl plus c double prime theta plus q prime theta whole square into variance of tx curl, that is equal to 0. Now just solve this expression by replacing expectation of tx curl with its form and get the variance of tx curl. For the probability model under one parameter exponential family, the log of the likelihood function is equal to c theta plus q theta into tx curl plus dx curl, and therefore del theta log of the likelihood function equal to c prime theta plus q prime theta into tx curl. Therefore here the likelihood equation is c prime theta plus q prime theta into tx curl equal to 0, or we can say this is equal to tx curl equal to minus c prime theta by q prime theta. Now note that in particular, if we take n equal to 1, the PMF or PDF, which is denoted by say f theta x, will belong to one parameter exponential family if f theta x can be expressed as e to the power q theta into some statistic t star x plus psi theta plus hx, where theta belongs to the parameter space omega, which is a subset of real line, and f theta x satisfying the assumption 1 and 2, which is already mentioned. Then, following the previous track, we can similarly say that here also expectation of the function t star x equal to minus psi prime theta by q prime theta. This implies the joint PDF of n independent random sample observations is here p theta x curl equal to e to the power q theta into summation I from 1 to n t star xi plus n times the function psi theta plus summation I from 1 to n h of xi. Now, This can be looked upon as p theta x curl equal to e to the power q theta into a statistic t of x curl plus c theta plus d of x curl with the choice tx curl equal to summation I from 1 to n t star xi, c theta equal to n into psi theta, and dx curl equal to summation I from 1 to n h of xi. Clearly, if we can express the joint PMF or PDF p theta x curl this way, then p theta x curl will belong again to one parameter exponential family. Now we consider the following interesting result. The method of moments and the method of maximum likelihood agree each other for one parameter exponential family distributions. Let the common PMF or PDF be f theta x equal to e to the power q theta into t star x plus psi theta plus hx, which belongs to one parameter exponential family. Then, based on a random sample of size n, the log likelihood function will be small lx theta equal to q theta into summation t star xi plus n into psi theta plus d of x curl, where xi denote the ith sampled observation and x curl denote the vector of sample realizations. Now, del del theta small lx theta equal to 0 will imply psi prime theta by q prime theta equal to minus summation I from 1 to n t star xi by n. But it is to be noted that minus of psi prime theta by q prime theta is nothing but expectation of the function t star x, and we have already obtained this. So what we got from here? The likelihood equation then gives us expectation of t star x equal to summation I from 1 to n t star xi by n, that is nothing but the sample arithmetic mean on t star x. So the likelihood function here gives population mean of t star x is equal to sample mean of t star x. Suppose this relation is denoted by star. But just observe the star. The star is nothing but the moment equation with respect to the random variable t star x. So here we get the likelihood equation is same as the moment equation, and our result this way becomes proved. Next we go to another interesting result. For any distribution in one parameter exponential family, the following two conditions holds. Number 1. Any solution of the likelihood equation provides a maximum value of the likelihood function, and number 2 is a solution of the likelihood equation, if exists, is unique. These two conditions holds for one parameter exponential family, and as a result of these two conditions, we can say that the solution of the likelihood equation, if exists, is unique, and it is nothing but the unique MLE. As a proof of this result, we can start from the proof of the first part. For the proof of this part, suppose theta curl be a solution of the likelihood equation. Then, from our previous knowledge of likelihood equation, we can say that here c prime theta curl plus q prime theta curl into tx curl equal to 0, which implies minus of c prime theta curl by q prime theta curl equal to tx curl. Now, minus of I theta, which is equal to expectation of del square del theta square of log likelihood function, that is equal to c double prime theta plus q double prime theta into expectation of tx curl, and this is necessarily less than 0 for all theta, as the prior condition of one parameter exponential family is that the function I theta should be necessarily positive. Now this implies c double prime theta minus q double prime theta into c prime theta by q prime theta is less than 0 for all theta, which implies for theta equal to theta curl also it is valid. But just observe that the second order derivative of log likelihood function with respect to theta at the point theta equal to theta curl is again c double prime theta curl minus q double prime theta curl into c prime theta curl by q prime theta curl. And from the previous steps, we can easily say that it is less than 0. So, automatically, the solution of the likelihood equation theta curl maximizes the likelihood function of theta from the second order condition of maxima minima principle. As a proof of the second part of the result, if possible, suppose there exists another solution, say theta double curl of the likelihood equation. Now, using the statement of the first part of the result, we can say that theta double curl also maximizes the likelihood function like theta curl. Now just think a function which is maximized at theta curl and again at theta double curl, then definitely there exists another solution of the likelihood equation in between theta curl and theta double curl which minimizes the likelihood function. But this contradicts the first part of our result, which says that any solution of the likelihood equation will necessarily maximize the likelihood function. Hence, our supposition regarding having more than one solution of the likelihood equation is proved to be wrong. In other words, the solution of the likelihood equation, if exists, is only one, that is unique. Now consider the following notes. Number 1. We know for one parameter exponential family distributions, Tx is the complete sufficient statistic. Also here, the MLE is the unique solution of Tx curl equal to minus c prime theta by q prime theta. These 2 points imply the MLE and the complete sufficient statistic Tx curl are in one-to-one relation. But we know by Rao-Blackwell-Lehmann-Scheffé theorem that minimum variance unbiased estimator is a function of complete sufficient statistic. This implies under one parameter exponential family, the minimum variance unbiased estimator can be obtained from MLE just by bias correction. Note number 2. We get the second order derivative of log likelihood function at the point theta curl equal to minus I function at theta curl under one parameter exponential family. So from here we can say that I function of theta equal to minus second order derivative of log likelihood function with respect to theta at the point theta curl equal to theta. This expression helps evaluate I theta avoiding mathematical expectation. In fact, the equivalence of the moment equation and the likelihood equation under one parameter exponential family is responsible for this happening. We illustrate this interesting matter through the next example. Let x1, x2, xn be IID normal 0 theta random variables. Then the log likelihood function is constant minus n by 2 log theta minus 1 by 2 theta summation xi square. As a result, the likelihood equation becomes minus n by 2 theta plus summation xi square by 2 theta square equal to 0, which gives the solution of the equation as theta curl equal to 1 by n summation xi square. This theta curl is the unique MLE of theta here. Next, consider the second order derivative of log likelihood function, that is equal to n by 2 theta square minus summation xi square by theta cube, and that can be expressed as n by theta cube into within bracket theta by 2 minus summation xi square by n, that is, this is equal to n by theta cube into theta by 2 minus theta curl. Now if we directly calculate the function I theta, that will become n by 2 theta square. But just note that second order derivative of log likelihood function L theta at the point theta curl equal to theta again gives you n by 2 theta square. So it is established through this example that the I theta can be obtained in second order derivative of log L theta just by replacing theta curl by theta. Next we go to third point under note. Let there exist an unbiased estimator Tx curl of the function g theta with variance attaining Cramer-Rao lower bound, then p theta x curl is of the exponential form and del del theta log of capital L theta, which is same as del del theta log of p theta x curl, can be expressed as k theta into within bracket tx curl minus g theta. This equality we get from the holding of equality in Cramer-Rao inequality, and this relationship gives the unique MLE of g theta as tx curl. Our last point of note is that our discussion can straightway be extended to multiparameter exponential family. The results are very much similar to those obtained under one parameter exponential family. For detail of this part, the reader can go through the parametric inference by B.K. Kale or theory of point estimation by Lehman. Next, we can discuss power series distribution family in the context of maximum likelihood estimation. Let a discrete random variable x follow a discrete probability distribution with PMF f theta of the form f theta x equal to some function ax into theta to the power x divided by g theta, provided x can take value 0, 1, etc. and the PMF takes the form 0 otherwise, where theta is positive, ax is a positive real valued function of x, and g theta is a positive real valued function of theta. Now, any discrete probability distribution of this form is called power series distribution. The corresponding family is called power series distribution family. As f theta x is a PMF at the point x, hence summation of f theta x over all possible value of x will give 1, and this implies g theta is equal to summation of ax theta to the power x over all possible feasible value of x, provided theta greater than 0. Now, with a straightway mathematical manipulation, we can get that expectation of x equal to theta into summation x ax into theta to the power x minus 1 by g theta, x greater than equal to 1, and we can easily note that the numerator under summation notation is nothing but the partial derivative of the function ax into theta to the power x with respect to theta, and as a result we get expectation of x equal to theta by g theta into del del theta summation of ax theta to the power x, by considering that interchange of summation and differentiation is permissible. With the simple manipulation, this way finally we get expectation of x equal to theta into del del theta log of g theta. Now, if x1, x2, xn be n random observations on x, then using method of moments, we get the moment equation, that is expectation of x equal to sample mean x bar, or theta into del del theta log of g theta equal to sample mean x bar. Suppose we denote this equation by star. On the other hand, the likelihood function of theta is L theta equal to product over function axi into theta to the power summation xi whole divided by g theta to the power n. This implies the log likelihood function of theta is constant plus summation xi into log of theta minus n into log of g theta. As a result, the first order derivative of log likelihood function with respect to theta gives summation xi by theta minus n times del del theta g theta whole divided by g theta. As a result, the likelihood equation becomes x bar by theta equal to del del theta log of g theta. Let us denote this equation by double star. Now it is easy to observe that star, which is the moment equation, and double star, which is the likelihood equation, are here same. And this implies the method of moments and the method of maximum likelihood coincide for power series distribution. From the discussion of this module, we learned the general structure of OPEF and the likelihood equation under OPEF. Interestingly, we realized here that the moment equations are identical with the likelihood equations under OPEF. The same thing happens for power series distribution also. Also in this module, we have obtained the MLE of binomial and Poisson distributions as particular cases of power series distributions.